Let's rejoin the conversation for part two of my interview with Dr. Josef Urban.
I sort of imagine again as a non-mathematician that mathematicians are, sitting in their offices with pencil and paper and writing out obscure theorems. But like everything else, it seems if we can get machines to help and it transforms the scale, just in the same way that an engineer working with a tall building, isn't using his slide rule and pen and paper to work out the stress at every joint in a steel frame of a skyscraper that's 2,000 feet tall. Right, they're running some program that in a batch mode examines all of those stresses together. And I would think that the same thing would apply to mathematics. And I guess now it actually does, that you're working on such hard problems that this could really change the process of doing theoretical or even applied mathematics.
Yeah, so indeed, like this was really something which people seriously doubted that Tom would achieve. Like they probably even first doubted that they would get the sort of proof that was like computationally supported, and then they very much doubted that he will get it formally verified. And all of that happened. And I would say what was also quite interesting. So I mostly work with this Mizar project that I might have mentioned or we will talk about. But sometime in 2011, I met Tom and I told him, well, you have a big project which is almost finished, and I have my technology which learns from the proof. So why don't we try it on your big project? And what happened about one year after that was that with Cezary Kališík, we got something like 40% of the lemmas, there were about 20,000 at the time. In that project, we could prove automatically by using some kinds of machine learning and combination with systems like eProver, Vampire, Z3, etc. So that would be like my add-on on like where Tom put it, right? Like Tom has worked hard in the sort of interactive theorem proving, like the formal proof verification. And what me and Cezary and other people, especially now on this big project, have been doing is to really try to automate as much of that work as possible.
Yeah, and maybe another thing to clarify is this is a really very exciting kind of marriage of technologies. I mean, theorem provers have been around for a long time, and they've, in theory, you might say, been capable of doing these large mathematical proofs, but they haven't been fast enough. And so the key thing has been improving their strategies. So just to really simplify it down, your prover could say, pick the smallest next rule that would transform some element of your current mathematical proof. But that might not be the right one to pick. There might be other metrics as opposed to just picking the smallest one. And it seems like people have started to almost exhaust those strategies. I mean, the major provers get better every year, but you've managed with machine learning of really learning the strategies of taking these simple, small steps in automated theorem proving and figured out how to pick the best strategy that gets you to the answer fast enough, but still using the mechanisms of automated theorem proving, of mathematical logic rather than statistics.
Yeah, so we do several things. Like this has been a large project. So what you are describing is what we call basically learning of theorem proving strategies. So you have somebody like Stefan Schulz, who creates an excellent open source automated theorem prover, and he even is great enough to define a domain specific language in which you can invent new strategies. And like Stefan, actually for his PhD thesis, he was doing machine learning, right? Like he's like the great grandfather of what we are doing today. It's just that he sort of got too much, I would say, sidetracked by the beauty of implementing eProver rather than by the ugliness of implementing machine learning. But for example, you can really readily take the interface, like the domain-specific language for constructing various search strategies that Stefan has in eProver, and do some sort of evolutionary or iterated local search algorithms for finding optimal or good strategies for sets of problems. So that's definitely very rewarding thing where some various kinds of machine learning work for you. What we did, I would say, even more in the sort of recent project is that we sort of replace this invention of the pre-specified blocks and written in the domain-specific language by a big blob, which is some black box statistical machine learner, like, for example, some neural network or some decision trees or just some logistic regression. And it turns out that plugging in a well-trained big blob like this with today's machine learners can do really a lot of things for you. So we have experiments where my student Zar Gertzel took the best strategies that we have developed in the sort of older evolutionary setting, and he trained on their proofs this sort of decision trees, basically, this big blob, this statistical machine learner. And even though the eProver that he was using was totally stupid, like it wasn't using any advanced strategy, term ordering, literal selection, it learned so well that it was beating the best invented predefined strategies. So it's really good fun how all these things interact now. It's really quite exciting.
Yeah, fantastic. So one of the questions that I often have about machine learning solutions is, they can find great solutions in particular spaces, but then what's the transferability when you go out of that space? So you found that, say, if you develop a strategy for all sorts of theorems about number theory, does it then, if you go over to group theory or some other area of mathematics, do those strategies also work for proving theorems with those axiomatizations?
Very good question, Adam. Excellent question. So different methods work differently. When I did the first strategy invention system, my initial intuition was that it will be, and I actually programmed it that way, that it will be proving different specialist strategies. Like my guiding idea was this evolution where you have the giraffe that specializes on eating the leaves from the high trees, and then you have the bat, and like all these different creatures, each of them taking its niche. But what happened to me is that the evolutionary mechanism developed a super strong generalist strategy that was much better than whatever the best pre-coded strategy could do. So
really like the evolution of humans, became the ultimate generalist and took over the world for better or worse. And you found the same thing with your algorithms.
yeah. So this was really quite interesting, and it's probably because, for example, on the Mizar problems, even though the problems come from a large mathematical library with many different problems, so you could say that this is really pretty universal, they are still encoded in a particular way. So, for example, the type encoding in Mizar leads to quite long clauses with many assumptions, with many like negative literals. So what I can imagine is that this particular encoding, even though you are talking about very general corpus, has still some particularities that are well handled by some particular kind of strategy. So that could be that could be one effect there. About the sort of statistical machine learners, that's also fairly interesting. So we have some which are really symbol-based. So they are looking like, is this now group theory? Is this topology? Is this number theory? Well, whatever. And those definitely will not generalize to other domains. But then what we did later is, for example, where we use just like an abstract tree of the formula, where we, about each symbol, only know its arity and to which other symbols, which are again just characterized by its arity, they are linked. And we characterize the abstract syntax trees by a set of walks of length 3 or 4, for example. And already this like very sort of anonymous abstract description gets us very similar performance as the one where we are using symbols. So that's quite surprising. And another sort of bit of information is that we also do it with a special neural network, which also totally disregards the names of the symbols. It only considers the graph, how they are, so how are the symbols linked together. And again, this graph neural network that we now have, it's probably the best thing that we have for machine learning guidance. So and we have actually done experiments when we have tested, like we have asked the neural network, what do you think is the name of the symbol? And quite often we can see some interesting sort of transfer. So for example, you have quite a lot of theorems like a duality between intersection and union, like some De Morgan laws, basically in Boolean algebras. So quite often it would guess that this symbol is union even though it's intersection, and this symbol is intersection even though it's union. Or you have some theorem about real numbers, like real calculus, and it would guess that it's complex numbers and complex calculus. So these methods do transfer to some extent.
Yeah, although it's interesting that it sounds like one of the things that you've done is to create some of the abstraction of the input yourself, right? By removing some of the symbols and just focusing on the structure. You've told the machine, here are the essential features of the domain, where this very broad domain to focus on that prevents it from getting itself into trouble.
Yeah. That's definitely the case when we did this abstraction by ourselves. When we do it via the graph neural network, it's sort of no feature engineering. That's the sort of buzzword that the deep learning community really likes. No feature engineering. And well, you could still sort of say that we are engineering the sort of architecture of the neural network, etc. But there, you are sort of, even this part, you are sort of leaving up to the back propagation, to the training of the neural network, basically.
Wow, fascinating. So I want to maybe shift gears a little bit, because kind of one of the enablers of this whole study that you've done is having a lot of the mathematics already formalized, right? So you can't prove a big theorem on anything unless you have lots of background information for the machine to do some search over to try to turn it into a solution for the question you've asked. So a lot of this work, I guess, is all based on work you've been doing a very long time on the Mizar library of formalized mathematics, all formalized in languages that the theorem provers can consume. Can you talk about Mizar and how that fed into the AI for Reason project?
Yeah, that's a nice question. So Mizar is one system in a bigger category of interactive theorem provers or proof assistants. And it's really an old project. It's one of the oldest. It started in 1973 in Poland by a guy called Andrzej Trybulec, who was a very good mathematician. He did PhD in topology, and he had trouble with various refactorings of his PhD thesis as he was adding new theorems and new stuff to his PhD thesis. He basically wanted to have some system that would assist him like once he had made some proof and now he changed slightly a definition or whatever, he wouldn't like the proof to go wrong, like to basically have some assistant or bookkeeper for helping him with that. And he was also very interested in linguistics. So he started to basically analyze the structure of mathematical articles. And according to that, he and his colleagues started to create a language that would sort of resemble, that would be formal, like a programming language, but it would still resemble how mathematicians are writing the formulas and the proofs. So they sort of proceeded in some sort of splendid isolation behind the Iron Curtain without being known too much by the sort of Western theorem proving community, which was sort of more into like computer science stuff rather than into formalization of mathematics. And in 1989, they decided that the system and the language is developed well enough that they will start really like a broad scale formalization of mathematics to sort of test the system as you go. Like here, Molto was experienced, not only doctrine. So you really need to go into more advanced things to be able to develop the system further and to see like what are still the problems of the system and the language, etc. And they got funded by, like after the revolution, also they got, for example, Office of Naval Research funding. And they developed quite early quite a lot of mathematics in the system. So I would say by the year 2000, they might have, I don't know, like 700 Mizar articles in all sorts of mathematical areas. They even, like this Office of Naval Research grant, asked them to formalize a reasonably advanced book by Dana Scott and his colleagues about continuous lattices. And I think by like 2002, 2003, they formalized like 60% of the reasonably advanced book. So it's quite a lot of mathematics. And the beauty of it for me was that not only it was mathematical, which I was sort of interested in, but also it was using quite common foundations, like basically first order logic and set theory. So I could quite easily translate it to automated theorem provers like eProver and Vampire, etc., and experiment with that. And yeah, and do the sort of machine learning stuff on top of that. So it's a project I sort of got involved to. I even did some formalizations in it to see how the formalization works.
Wow, this is fascinating. I actually had no idea about this history. I should have read up before, but to think about this formalization occurring, starting back in the 70s, so long before any of the modern theorem provers that I'm familiar with, like he even got started. Mathematicians were doing this groundwork, anticipating that all of this stuff would be very useful. And you've been able to leapfrog off of this big library, and I guess transform it too, right? Because it wasn't written in a modern knowledge representation language. You had to translate this into TP-TP or other languages that the theorem provers actually use today.
Yeah. So that was like a big part of my PhD thesis. I really sort of wanted to see how much of the manually, like it's never completely manual when you are proving things in these interactive theorem provers. Like you have some small efficient automation in there, but I basically wanted to see how much of the theorems, which at the time could have been like, I don't know, 30,000-40,000 theorems, the automated theorem provers like E and Vampire can prove. So indeed, like I needed to translate it, which for Mizar wasn't so difficult. Like I said, it's basically first order logic. And then I ran the automated theorem provers, and it gave me some numbers like gave me like something like 40% if I could like use the premises that were manually selected by the author of the Mizar proof. And that was really quite surprising, like, because, for example, the Mizar people really didn't believe in automated theorem proving. So they were very skeptical that the automated theorem provers will be able to prove anything useful. And the 40% number really surprised them as much as it surprised me.
Well, that's always satisfying, where you can come up with a kind of unintuitive result where there's a community that doesn't think something will be successful, and darn it, you show that it actually does work.
Oh, yeah.
We'll pause the conversation there and return for part 3 of my interview with Dr. Josef Urban.